let's see, we just finished, or we were working on this Geneva mechanism problem. And let me clear my spaces. We're looking for the acceleration, angular acceleration of disk S, right? Because this mechanism comes in and this pin makes contact with this, this wheel. And they tell you at the instant when phi is 150 degrees, determine the angular acceleration of the disk, right? So you've gone, this pin is now into the groove somewhere, and it's now starting to rotate disk S. We figured out, oh, we have the general acceleration term, right? The total acceleration of P, point P, is equal to the acceleration of P prime, this conceptual point that's located on the rotating frame of reference, P with respect to S, and then the Coriolis acceleration. And what we've done is we built up, or we've basically taken each of these terms from the equations in the book, and we've built up what they are. Remember, we did the previous problem where we had the angular velocity calculated already. So we already had some information from that. So if you were starting from scratch, you'd have to basically do all the work we did in the last sample problem to get to this point. Let's see. Oh, yeah, so we found A of P. And we found A of P prime tangent, and the normal component, oh, here's the normal component. I didn't underline that. The normal component of P, A of P prime normal, right, is this, this direction here, 42.4 degrees. And then the tangential is obviously 90 degrees to that. And this contains the angular acceleration of S, right, which we don't know. We just know the multiplier by it. And then A of C, acceleration of C, right, is just 2 omega cross product with the radius. We know our angular velocity, omega S, from up here, and we know our velocity, V of P with respect to S. So we get an acceleration, a Coriolis acceleration of, I don't know why I said A of C, 3892 millimeters per second squared, and that's in this direction, perpendicular again to the vector that we're taking the cross product with. We made some comments how A of PS is parallel to the slot, and pin P is moving in a straight line, right? The slot's cut into disk. S is a straight line, right? So it looks like this is basically A of the acceleration of P with respect to S again is looking like it's just moving in a straight line if you're an observer on S, right? So this is acceleration of P with respect to S. And then the Coriolis, oh yeah, the Coriolis direction, how you got that. So we can put these terms together now. This is where I left off. So let's just plug these terms in. I'm going to write them generically using an angle format, and then we can convert them into I and J components, actually. So here we've got 5,000, angle 30. There it is, 5,000 angle. All right. The normal and tangential components we have up here, so 617.6. This is at an angle of 42.4 degrees. Plus, we've got the tangential component of that, 37.1 alpha S, and an angle of 42.4 from the negative vertical axis. Oh, and of course I'm going to run out of room. Oh my God. I don't understand how I can fit this on one line in my notes. And then A of P with respect to S. What the heck? Oh, here it is. We don't know this, right? This is at 42.4 degrees. And then we've got 3892. Oh, 92. And an angle like this, 42.4 degrees. All right, let's see. Before I do anything else here, there's two things you can do here. You can look and see that A of S is perpendicular to the slot, right? And we can just equate perpendicular terms to find that. But I want to do this in, I want to sort of write out the vector form just so you can see where all this stuff is coming from. Let's see, AS, AFPS. Because you can get two equations, two unknowns, and we can solve for everything. So we got 5,000 angle 30. This is going to be 5,000 times, so notice this angle, right? It's down, it's pointing down in the negative direction. So we've got cosine 30 for I and sine 30, negative sine 30 for J. Let's write cosine 30I minus sine 30J. Maybe I should distribute it, I don't know. We've got six, I'm just going to round this to 618. And we have, again, we've got the direction, we've got negative cosine 42.4 minus sine 42.4. Oops, I got to put the I's and J's in here. Trying to avoid too many parentheses. I'm going to keep adding terms on here. So we're clear. That's a continuation. Oops, plus 37 point, what do I have? 37.1 alpha S. This is, oh, here it is. We have for the X direction, you can take the positive sine of 42.4 and the cosine is the, or the Y direction is the negative cosine. So we have sine 42.4 I minus cosine 42.4 J. Oh my God, I'm running out of room so fast. Acceleration of P with respect to S. Let's see, this one, 42.4 degrees. So we've got a positive cosine 42.4 plus a positive sine 42.4 J. Oh my God. Finally, we got the 3892 term. And that's pointed up and to the left. So it's a negative. Remember, you're given this inside angle between the vertical axis. So negative sine 42.4 I plus cosine 42.4 J. All right, this took a while, a lot more room than I thought. All right, so we can basically look at this and separate out our I's and J's, and we can write two sets of equations. I'm just going to write those equations because it's going to be a mess expanding it all. We wind up with 25.02 alpha S plus, remember everything else is basically numerical, right? Well, there's in functions with respect to APS, and then everything else is you've calculated out, plus 0.7385. This is A of P with respect to S, right? So this equals 7410.8. And then the J direction, these are directions. You wind up with 27.4 alpha S minus 0.6743 A of P with respect to S. And this is 4957.3. Oh, and it looks like I forgot to write down the solution for A. Well, I mean, we're basically looking for alpha S. If you solve these two equations, two unknowns, you wind up with alpha S is 233.3 radians per second squared. And if you look at the direction this is going, right? I mean, you can kind of intuit it from the problem, but you can also see from the vector. Where's the vector? Right, 37.1 AS. It's angled downwards like that, right? It's accelerating clockwise. So that's the direction. You can also use vector format to do this, and that's what your textbook does here. And that's the reason I did this. I did this separately in rectangular coordinates, basically vector notation. So I wanted you to see that multiple ways of solving this. Let me unhide these so I can project. Here they draw a vector diagram, so you can see this vector diagram. So it's probably good to go through this problem and look at the, if you're not following, like if you don't follow the vector portion, or if you don't follow the algebra, go look at the geometry, right? If you don't follow the geometry, go look at the algebra side by side, so you see them together. I mean, I tried to do that at the beginning when I set up the problem, but this is one of those problems where it gets a little dicey, right, on paper. So these diagrams are nice that the textbook provides. There's this one, and where's the, yeah, they just, here's where they do the components of acceleration perpendicular to the slot. So if you actually work this out in vector form, right, you notice that, okay, there's basically, what are the components perpendicular to the slot? And they work these out, right? 37.1 AS plus the 3890 minus the 5,000 cosine 17.7. So geometrically, it looks something like this, right? This is what we had when we wrote those components out with the angle notation. All right. So that's chapter 15. And what I want to do is work on chapter 16, but I want to go back here. Did I put a, no, I didn't. Okay. I updated the homework. I didn't realize the homework was visible on McGraw-Hill, even though I hadn't posted it in Blackboard yet, because I hadn't looked to see how far we were going to get yet. But the homework for chapter 6 is only a few problems. It just covers section 16.1. So there's just 8 questions. So use this homework. If I think one of you might have started the other homework, or you went into it at least, because I didn't see any answers to it. So I turned that off. Don't use the other homework. Just go to 16. This homework labeled 16.1. Zoom in a tad here. So that's the one you're going to use. All right, so let me put these other notes away and we'll start chapter 16 here. Oops. Okay. All right. So chapter 16 is rigid body kinetics. So we dealt with rigid bodies, and we also dealt with similar concepts to this in earlier in the chapter, or sorry, not earlier in the course, where we dealt with systems of particles, right? Except in that case, the systems of particles were free to sort of independently move. Now we have rigid bodies, and the concepts are going to be fairly similar. So when we go through this, I think you'll see that there's a lot of similarities between this and groups of particles. We're not going to get to 17 and 18. So we're looking at plane motion of rigid bodies, and rigid bodies which have a plane of symmetry with respect to the reference plane. So think about if the sheet of paper you're looking at is the reference plane, the body is symmetric on top and on the bottom of that plane, right? It doesn't have to be symmetric. Like, you don't have to look at it and see symmetry in the cross section, but the cross section itself is symmetric about the plane. Yeah, so this is this is the same approach. Rigid bodies being made of large number of particles, and this way we can use some of the concepts from chapter 14. Specifically, they're citing some of the forces is mass times acceleration, and some of the moments about the center of gravity is equal to the linear momentum about the center of gravity. All right, rigid body acted on by several forces, right? This is what it looks like. Notice the center of gravity of this body, and it's acted on by these forces. We're using the center of gravity as a reference point, basically an origin point on that body. And the assumption here is that it's just made up of a large number of particles, right? So you could write a unit vector, a position vector, from the center of gravity to any position on here, right? Any particle, this delta mi, right? This infinitesimally small mass, which is a particle. And then we're going to use this idea here too, that all these forces, right, are equal to mass times acceleration and angular or linear momentum about that point of center of gravity. Let's see. Again, this is with respect to the centroidal frame, right? So the centroid being the center of gravity, in this case, the same thing as long as it's a symmetric uniform body. Here's a rigid slab in plane motion, right? So again, if I'm looking at this slab, my assumption is that, okay, while it doesn't look symmetric to me any way I slice it this way, it's symmetric about the plane, the x prime, y prime plane, right? So if it has some kind of thickness to it, it's basically, it's like you took this shape and extruded it equal amounts up above and below this this x prime, y prime plane. Let's see. Angular momentum, basically the sum of the RI's VI delta M's. This gives us a new term here. The well, it's not that new. I mean, it's the moment of inertia, right? It's a mass moment of inertia, however. So it's got the mass in it. So the mass moment of inertia. I mean, before we dealt with mainly moments of inertia in, as a geometric quantity. And just that was just assuming, you know, homogeneous mass, but now you've got the mass moment of inertia in there. Oh, this is a linear momentum, right? Or angular momentum. You take the derivative of this, you get the acceleration, right? Angular acceleration. This is what I was talking about with symmetry. Yeah, not valid for asymmetric bodies or three-dimensional motion. So, and that makes sense, right? Because we're taking this rotation within a certain XY plane. So now we can say that the motion, right, is completely defined by this resultant, right, about G of the external forces. You've got some of the forces in, you can break this down into X and Y components, right? Some of the forces in the X and Y direction are equal to mass times acceleration in those directions. And then the sum of the moments, right, generated by those forces about G, the centroid, is equal to the mass moment of inertia times the angular acceleration, right? Yeah, this is just talking about equivalence and equipolant. Where's the other diagrams? Here it is. The external forces, you can write this again. You can look at this and you can write this as a translation, right? And rotation. That's kind of the same ideas we've been doing, right? You've got these forces, you're resulting in a translational component, right? Which in this case also happens to be an acceleration, and a rotational component about the center of gravity. So that's how we're doing this. Yeah, this is just basically telling you that, remember that axiom we learned way back, how a force acting along its line of action, you know, these two forces are basically the same, right? Force, as long as it's along the same line of action. This is saying that these concepts here in this chapter basically prove the principle of transmissibility, right? Because you're using this, if you do the analysis on something like this versus something like this about the center of gravity, you're going to wind up with the same answer, same set of results. When they do proofs, though, they never use numbers; they always use variables, and it's it's very mathematical. So let's see, free body diagrams. So be sure you draw your free body diagrams. You can see here we've got our force diagram, right? And then our kinetic diagram. And this helps you sort of visualize, okay, forces equal MA, and then, well, it's not forces, but it's sum of the moments about G give you the rotational component, the I alpha. Free body diagram, same as statics. I don't know why there's, oh yeah, I did this. First of all, isolate the body of interest, right? You're given this example down here. You've got a some kind of gear, or I don't know, not gear, drive shaft, and it's got a belt on it. And obviously you're going to isolate this body of interest, right? And you're going to go ahead and draw your axes. I put this over here just to denote, you want to have, because we're not just doing some of the forces, right? We're doing some of the moments. You've got your X positive, your Y positive, and, you know, again, we use the counterclockwise direction as positive. So a lot of times you'll see just a little graphic like this next to a free body diagram, just indicating those are the directions that the person that drew the diagram considers to be positive. Obviously add in the applied forces, and then replace all supports with forces too, right? Now notice this is not, we don't know anything about G except the center of gravity, so we're just replacing this with weight. And this is tension. We've got a distance. Yeah, dimensions. Draw your appropriate dimensions. Kinetic diagrams. So with kinetic diagrams, you're going to have something like this, right? We're taking and equating the free body diagram to the kinetic diagram. And we do the same. So this is what I was talking about. You're going to see in the book, and I'll use examples where I draw a little axis like this, right? This is Y, this is X. I've been doing this for a while. Yeah, isolate the body of interest again. So now we're looking at, okay, what's the mass times acceleration, right? Let's put those components in. So this wheel, or whatever this is going to have a component due to these forces of mass times acceleration in the Y and X direction, right? It's also going to have a rotational component. Notice that your book uses a subscript G. Specifically, now we're denoting the sum of the moments about G. Now, when you do an analysis, you can take the sum of the moments about a different location, but you need to account for that in your terms to the right, right? It's not just the moment of inertia about G anymore. You've got to adjust that with an adjustment term, and we'll see some of that in some of the example problems. Yeah, you typically draw these things from the center of mass, right? All right, so here's an example of a bar. We've got a bar mass M, and a known force is applied here at the bottom. Notice the center of gravity. You're going to see this show up on objects, or you may have to calculate the center of gravity. This is where centroid calculations come in, right? If you know, if you're told that the mass is, if you're not told anything about the center of gravity, you have to figure that out. And a lot of times you'll just assume, you'll be told, you know, assume it's a uniform object of material, whatever. And geometrically, you find the centroid and figure out where that is. So let's look at the free body diagram. I have the diagram over here. So we're going to isolate the body first. And we're going to put some axes in. So what's our definition? We've got, oh, I don't know what happened over here. X, Y, and counterclockwise moment. Let's look at our applied forces. Well, at C, we've got a pin joint. So we're going to have a CY and a CX. Down here at B, we've just got force P. And then we've got the force of gravity, right? The weight of this thing acting at the center of gravity. Because we were told it has a certain mass. Yeah, dimensions, we got to put that in. And then we draw our kinetic diagram. So our kinetic diagram shows acting at the center of gravity, the center of mass. We've got a mass times acceleration in the X, in the Y, and then we've got an inertial rotational component about that centroid, right? All right, what's this? Oh, there's another example. Here's a drum, 4-inch radius, attached to a disc of 8-inch radius. It tells you the combined mass of 10 pounds. It tells you there's a cord attached, and there's a force of 5 pounds applied. Now notice here, the coefficients of static and kinetic friction between the wheel and the ground are given, right? So what do you have here? You're having some information on, obviously, the geometry. You're given that. You're given the mass. You're told there's a force acting on this, but you're also told there's force of friction involved, right? You're given this information. So now you know, okay, well, there's some kind of force of friction I need to account for here. So let's see what that would look like in a free body diagram. So we're going to isolate the body, draw our axes, and put the forces in. So our body looks like this. And the way the forces are acting, we've got the force P acting up on the center right here. We've got the weight acting at the center of gravity. Notice the little G. Right down. That's the, what is it, combined weight of 10 pounds, I believe it is. Now, down here, we have a normal force and a force of friction. So, I mean, you can draw this. Let's see, if you're pulling up, you think, okay, the direction of motion might be this way. They just do generically a force of friction. Make sure you put your dimensions in. And then we've got a kinetic diagram here. So we've got mass times acceleration acting at the center of gravity. And then notice we've got I alpha, right, the rotational component, um, mass moment of inertia times the angular acceleration, right, acting around the center of gravity. So this would be our diagram to set up the problem. And then from here, you can start setting your forces equal to MA, right? You take your X forces, set them equal to MAX, your Y forces, set them equal to MAY, and then your moments, right? So look at the sum of the moments about G. We're going to have a force P at a distance of 4 inches, and we're going to have a force of friction at a distance of 8 inches. Notice the weight doesn't do anything for the mass moment of inertia term. It just it's at 0, right? Here's another problem. I think this is the last one in free body examples. We got a ladder here, AB, and it's sliding down the wall as shown. So it's got a certain velocity. It tells you the wall and floor are both rough. Draw the free body diagram and kinetic diagram for the ladder. So here we're not given anything else except for the geometry and the velocity, and we're told the wall and the floor are rough. Now, you know, in a real problem, you'd obviously be given some other information to solve it. But from the geometry, we can figure out the center of gravity of this thing, right? Which is, the assumption here is it's a uniformly distributed mass ladder. So we're going to say the center of gravity is right in the middle. So let's see what that looks like here. We're going to isolate the body, draw axes, and put in our applied forces. And then don't forget, replace any supports with forces. Make sure you include dimensions and the kinetic diagram. So here's what it looks like all in one shot. First of all, we recognize that the center of mass here is right in the middle, right? 0.225 meters and 0.225 meters. So we've got the force, the weight, right, which is a force acting down at the center of gravity. We got to replace each of these surfaces. We've got up here, we've got a normal force, and we've got a frictional force. Down here, we have a normal force, and we also have a frictional force opposing that, right? So notice in this case, we actually did draw the friction opposing motion. You know, motion is in this direction to the left down here, so the friction is going to act to the right. Up here, motion is down, right? So friction's opposing that going up. And then we have our axes, and we have our kinetic diagram, which just shows this is supposed to be, looks like they could have moved this down a little bit. But this is, again, about the center of gravity. You've got your MA terms, Y and X direction, and then you've got your angular inertia term. All right, sample problem. I think we can probably start this. Oops. We have a van with a forward speed of 30 feet per second. The brakes are applied, causing the wheels to stop rotating. The van skidded to a stop in 20 feet. So this is like, I don't know, some kind of special ops A-team van. Determine the magnitude of the normal reaction and the friction force at each wheel as the van skidded to a stop. So the strategy here is that we're going to take a purely translational approach to this, right? We're saying that this van, right, think about it, the wheels basically lock up and it's skidding. It's just translating across. So there's really no angular acceleration. We're going to assume uniform acceleration, right, from the moment it put the brakes on to the time it stopped. And we'll draw the free body diagram and the kinetic diagram and put together the equations. Remember, we're going to have normal forces and coefficients of friction on the wheels. Let's see, magnitude of the normal and the friction force. Yeah. So we don't actually need well, we're not given the kinetic or the coefficients of friction, but we will be able to find that. So let's look at setting up this problem. Again, we can set up this problem and we'll go as far as we can. It might take me that long to draw a van out. All right, so let me draw this free body diagram first. So I'm going to have a van. Let me replace some of my forces here. So we're saying that our tires are basically locked up. We've got a normal force acting at each tire. Let's put NA and NB. The center of gravity is given. And we have dimensions for that as well. But let me just draw a W in here for the weight. Let me put some dimensions in here. This is our 5-foot distance. I'm putting them on the top just to keep them out of the way of the, and this is 7 feet. And we also had a 4-foot height from the ground. Oh, I need to put the forces of friction in here. That's why I drew my dimensions up here. This is the force of friction of A acting on tire A and the force of friction B, right? So now we've got all our forces on this thing. We got the weight, got the normal forces, and the forces of friction that are opposing motion, right? And let's just draw our little, I'll draw our axes in red here. Y direction, X direction. All right, these are all the positives. Let me draw the van out again. I'm just going to draw the kinetic diagram here. Not as consistent. This looks more like a bus. I don't know. Center of gravity. Let's just put feet, 4 feet. Let me draw my MA here. We're just using the bar for the average acceleration. Now notice, one thing is the forces of friction are opposing motion, and typically the net force and the acceleration are in the same direction, right? We don't have a force acting to the right, so we can be pretty confident our acceleration is pointed backwards, right? Now, in another type of problem, you might not know the acceleration, so you just draw it in one direction and make sure when you solve, you watch your signs, you account for these things. But here it's pretty intuitive that we're going to have that. Recall v squared equals v naught squared minus 2ax. These are average velocities, right? We have an initial velocity, we have a constant deceleration, we have a distance, and we have a final velocity, right? So we can rearrange this. This is just from what chapter, I don't even remember, it was 12 or 11. Over 2x. Remember the final velocity is 0, comes to a stop, right? Skidded to a stop in 20 feet. So what do we have? We've got 30 feet per second. These are just the equations of motion. And then we've got 20 feet. Let's see. Technically, let's see, v squared minus v naught minus 2. Yeah, so this is 22.5 feet per second squared. This is the acceleration. Now we know the acceleration is pointed backwards, right? And we'll account for that when we do our sum of the forces. You know what? I might as well write them down because we still have time. So let's write our equations. Sum of the forces in y is ma bar y, right, in the positive y direction. Let's just draw an arrow. What do we got? We got NA plus NB minus W equals 0. Next, we'll look at some of the forces is MAX. In this case, all our forces and acceleration are pointing backwards. So we've got a FA plus FB, right, negative, equals negative MA. So, I mean, you could just rewrite this as FA plus FB equals, right, the negatives are going to cancel each other out. And then equation 3 here, we've got sum of the moments. If we do sum of the moments about the center of gravity, we're going to have a bunch of forces to consider. I can simplify this problem by taking the sum of the moments about a certain point, like A or B, but I need to adjust my inertial term. And let's look at what I got here. I've got sum of the moments. I'm going to take it about A. All right, let me just write this term out and then we'll be done. It's not equal to 0. It's going to be I bar alpha plus MA bar D perpendicular, right? We've got now we've got, instead of just around the center of gravity where these things are, these terms are not important. Now we're taking it about A. So we've got to worry about that term. We'll just pick up here next time and we'll start working and canceling terms and finding what to substitute in for these things. And that'll include friction. All right, so are there any questions about anything?